the unobserved component model example on the daily time series of electricity loads. So I just copied the content of last lesson in a new one. So we will just correct or add things to this one. So what we did last time, of course, you may want to have some time for loading the data and copying what I already copied. So basically we wanted to work, we worked on hour number 17, so 5 p.m. Well, this is the plot. It's really not that necessary. It's just the plot of the last 1 year and a half, I would say. And this is the time series we were trying to model. It's the same time series we were modeling also with ARIMA. So I kept the ARIMA here handy in case we want to do comparison. And I suggest you also load that lesson 9 because we can steal the holidays creation functions that we wrote to use it here as well. But going back to what we did last time, we already built a model for this time series, but we noticed a couple of problems. So this was the model we did last time. So we used the local linear trend, but probably if I go back, I remember, for example, the variance of the slope was virtually 0. So the slope is probably constant. We could even fix maybe the slope to variance to 0, or just estimate. It doesn't change much. But more importantly, we used the dummy, stochastic dummy seasonality for the 7 days, so the weekdays seasonality. And we used the first 10 sinusoids for the within-year seasonality. But we noticed that probably 10 sinusoids were too few because there was a lot of seasonality still or caught by the trend. So the trend was moving with a seasonal pattern of every 365 days. So probably 10 sinusoids are too few. Indeed, I usually use on this time series about 16 of them. So we can just start by changing this number to 16. Of course, the state vector increases by 12 variables. So it will be a little bit more heavy to estimate. I mean, running the Kalman filter is a little bit heavier. And probably if you go back also to the seasonality of the Italian electricity time series, we probably have to put also some more abrupt fixes for like winter vacation and summer vacations, which tend to move very abruptly. The time series and the sinusoids are not very good for abrupt changes. They're better for smooth changes. And we decided to work starting from 2021 for a couple of reasons. One is for a matter of not waiting too long for the estimate. And the other reason is because of COVID, of course, that had an impact, which I don't think would show up in our, let's say, late part of modeling forecasting, but probably has some impact. And so I just modified this model. You can do the same. I suggest that you should copy everything from the last lesson. And here were initial values. Okay, we already estimated that, so probably we could exploit the previous estimations for better initial values. But anyway, I didn't save them in any place. So let's just use the same initial values. A couple of things about initial values. As I told you, initial values in theory are not that important. In practice, they may be important because if you miss up too much the scale of these values, then you can go very close to infinity or something that is not numerical treatable, and so you will get problems. Another reason is that, of course, the better the initial values, the quicker will be the optimizer to reach the optimum. So usually what I do, but you probably already understood that, is that I just compute the variance of the time series, which anyway is some kind of upper bound of all these variances. Actually, I would say it's an upper bound for the sum of all these variances. But many of these variances are much, much smaller than that total variance. Of course, from a, let's say, a puristic point of view, this is using the data more than once, but we want to have things that just work, so it doesn't really matter if we use the data to produce initial values. So usually the level is closer to the dimension of the original time series. Of course, this is the level, the variance of the level shocks, so the shocks that make the level evolve. Of course, they are much smaller than the variance of the time series, but as I told you, we should relate as a unit of measurement everything to that. The slope, actually, I remember that the slope we estimated had a variance which was virtually zero. So actually, this is of course a much smaller number, but it could even put a smaller. Also because remember, at zero variance here, we cannot afford a zero variance because we're modeling the log, of course, and the log of zero doesn't exist. Well, it's minus infinite, which is not a proper number here. But of course, we can put arbitrary close to zero numbers, and maybe I could even divide by much larger number, because this was really virtually zero. So it's an information that I remember, we can exploit it here. And something similar happens for the seasonalities, in particular for a very slow varying seasonality of within year seasonality. This was also virtually zero. So again, we can set it to a very small number. It doesn't really matter how many zeros I put, just put many zeros, because it was very close to being zero. And finally, instead, this is the observation noise variance, and that's more closer to the variance of the original time series, because you added that noise to the signal. So the unit of measurement is closer. And so, for example, in this case, I just divided by 100. So these are just like sloppy guidelines for determining some decent initial values. Okay, here we changed the number of sinusoids that we're using. So the number of state variables has increased. So let's check if this update function is still properly written. And of course, the first two lines have to do with the trend, and they're fine. We're just placing the first two variances into the first two diagonal elements of Q, and this is still good. It's still good that the third line, which is placing the variance of the within week seasonality to the third element on the diagonal of Q. And actually, it's still good also the next line where we write on the diagonal of this Q matrix, excluding the first three rows and columns that we already have signed up here. So written in this way, actually, that was a good idea, because I could augment the number of harmonics, and I don't have to rewrite this update function. And of course, the H is also properly written, because it's just one variance, that it's the element we call var epsilon. In all cases, we're taking, of course, the exponential as you know why. So this is fine. Here, it will take a little bit more of time with respect to last time. And still, this is not a final model, but because we're still missing all the, let's say, holiday dummies. But before building the holiday dummies, I want you to compute what we call the auxiliary residuals. So the auxiliary residuals were so the smoother applied to the disturbances and to the observation noise of the system. So we're estimating those disturbances based on the data. We kind of saw that thing 2 lessons ago. And that's according to which of the estimator, which disturbance you're looking at. If you find very large movements in those disturbances, then you find out some outliers, or if you find them in the epsilon estimate. But if you find them in the disturbance of the state variables, then according to the meaning, so the behavior of the component, the interpretation is different. As I told you, if I say a large value of the disturbance in the level equation, that means that we have like a jump. And I showed you how to fix that using regressors. And if we see that in the slope, we see a big change in the slope. So again, I showed you how to use that ramp to fix that. So actually, we will be adding the holiday dummies, but what I want you to show is that probably we are able to find the holiday days, the holidays, just by looking at auxiliary residuals. So this is basically what we estimated. It's kind of similar to last time. Large variance for the what we call the eta disturbance, zero variance for what we call the zeta disturbance. So the slope is not changing. We don't know the value actually of the slope. I don't remember. It was, I think, slightly negative, meaning that the consumption of electricity was, I think, slightly decreasing in time. And then we have a small variance of this within 7 days seasonality, which means it evolves, but it evolves very slowly. And actually zero variance for the sinusoids, meaning that that variance, so the within year seasonality, it's not changing, which is fine because we're just working on like 4 years or 5 years, almost 5 years, 4.5 years of observations. Of course, it's very hard to find changes of the within year seasonality in 1 year, in 4 years. Maybe if we use like 10 years, we have 10 years. Actually, this data start from 2004. I think the Nord Pool data are much longer. I think Nord Pool was born in 92, I guess. So you have really long time series, probably too long. I mean, the world changed, so it's not always a good idea to use all the data anyway. But so on 4 years, I expected this to be very close to zero, and indeed, I also put an initial value that was very close to zero. But anyway, this is what it results. And again, instead, the epsilon, so the error that sum up to the signal, that's much larger, in like 1.7 million, so more in the unit of measurement of the time series, as expected. If you try to reason about that, I helped you to do that, you can kind of come up with this conclusion. I mean, the dimensionality, the relative dimensionality of these quantities is not that strange. It's not that unexpected. Anyway, so the next step I want you to do is not just carrying out the state smoother, which it's fine to carry out because we will also want to see how the components change it. For example, by making more, by allowing more harmonics in the within year seasonality. But as I told you, I'd like to also have the disturbance smoother, Why the disturbance smoother? Because we want the auxiliary residual. So we want to see if there are like abrupt changes in any of these disturbances. And I guess if we want also, and we want them, the observation error smoother, we have to put, I would say, the signal. I don't think we need any filter. So now it's running the state smoother, the disturbance smoother. Okay, we are prepared to this warning. We're using many, I mean, all this vector gets infinite variance. We didn't change the variance, the initial variance of any of these components. So we start with a large vectors. If you go into the more, this is the dimension of the state vector. So it's pretty huge. And all of these components are non-stationary, and we're initializing them with an infinite variance. I didn't show you that because it's automatic. But if you check the P1 inf matrix, you will see, well, maybe just steal the diagonal. So you see, it's all ones, meaning that all these components receive an infinite variance at the starting point. So for t equal to 1. Of course, that's a big uncertainty we set up in the model. And so, as I told you last time, the initial values of these components are really not much reliable. But I mean, they're just the initial ones. So where is it? Here. So this is what we did. We did this. Okay, we can check out just as we did last time. We can plot the time series, which we can steal from the model. It's there. We can plot together once the smoother of the trend, so the level. Maybe give it a different color. I mean, still, I'm not very much satisfied by this trend. If you look at this trend, it's still picking a lot of seasonality. Especially, look at this. It looks like as I told you, for the Italian data, we still have problem with this August vacation and the winter vacation. We will be fixing them with dummy variables. Okay. The model will probably work decently as a forecasting model, but as an extraction of components, this is still bad. I mean, it's fine. I mean, it's following too much the data. So it's like the sinusoids are really not doing all the work we're asking them to do. We can see if we can fix that in some other ways. Yeah. And of course, we can also check especially the within year seasonality, which, if you remember, we have to sum up all the, so what was it? So we have to sum all the quantities starting from, so we have the first two, level and slope, and then we have 6 within week seasonality, and that makes 8. So starting from the 9th, we have to, well, we can just go up to the number of columns or yeah. So to the end, but we have to jump by 2 because we needed to just take the first of the 2 sinusoidal components. And then, of course, we have to sum all this by row. So row sums. This is the, I mean, yeah, this is the effect that we're using these sinusoids, which are not directly a component, but they sum up to make a component. So this is maybe And of course, this is not a line because it's not a time series, so we can just and this is the sinusoidal component. I mean, it's not as expected anyway. So it's not working that well. But anyway, let's pretend it's this model is okay. What I wanted you to see is could we maybe identify the holidays, the relevant ones at least, by looking at the auxiliary residuals. So holiday would represent just additive outliers, like it's Wednesday, but it's a Wednesday where nobody was working, so probably the load of electricity is going down, and so what we expect is just a big shock epsilon of negative sign. Okay, so that we can analyze by using those auxiliary residual for so auxiliary residual for epsilon. And if you remember, we can you can compute them using R standard, which is a generic function in R, and passing the smoothed values, of course, the smoothed disturbance that we computed, and ask for it's called Pearson, right? Strange name. No, smooth. Sorry, I call it smooth one. I didn't call it. So let's just plot those residual. And as you see, there are many moments which have very extreme negative values. We may just now like make a list of this. Actually, we should find the dates because now the dates are canceled, but we have the data frame with the dates. So if we find, if we transform these extreme values into their respective dates, we probably are going to find their all holidays. So, for example, we could just select, I don't know, all the values that are, well, maybe they're in excess with respect, in absolute value with respect to, I don't know, 3, for example. 3 could be a good value. So, so all indexes. So let's create a vector with the indexes of the additive outliers. So we can just go with which are apps in absolute value. So the absolute value of this is larger than 3. Maybe we could even be more like 3.5, whatever. Let's start with this. And then let's try to okay, I wrote it wrong here. Epsilon, no, Eps for epsilon. Sorry about that. Okay, so let's just turn this into dates. We can just use the WT. Yeah, we have the dates here, so we can just extract them. So we can go WDT, we extract the dates, and we select them at those indexes. And let's analyze those dates, and probably they are all or almost all holidays. I don't know, this could be Easter, I'm not sure. Well, the 1st of June, again, it depends. In Italy, it's a holiday on the 2nd of June, but if the 1st of June was like a Monday, then this is also some holiday. This is, for example, a holiday in Milan, which of course is a good part, and in the Milan area, which is of course important for the consumption of electricity. This is the, this is the day before the 6th. This is again a bridge day. I mean, we can kind of find, this is, sorry. No, it looks like they're close to holidays, but they're not exactly holiday. I mean, this is like in Italy, the 25th of April is a holiday, and this is the 24th. The 1st of November is a holiday, and this is the 31st October. It looks like there's kind of lag between the two. It shouldn't be, because the lag, as I told you last time, would be just if I work on the state disturbances. Of course, the state disturbances are having effect on the next day in this case, but the Pearson disturbances, so the epsilon, is having an effect, an immediate effect. But anyway, so this is Christmas. Of course, we could check also all the Easter. Well, actually, Easter, we have it here somewhere. So, for example, we're working on between 2000. Okay, sorry, I'm not using. So that's why it's not working. I did a mess. We didn't use all the data. We used. So that's why we use the data starting from this date. Okay. So I'm selecting the wrong dates. Okay, so that's basically why it's not. It was close because probably it started, from the 1st of January, and we started also from the 1st of January, but of course the holiday kind of changed it. We were close to holidays. So we have to select just the parts of the WDT data sets. So we can do this way. Okay, good. Or we can use, maybe it's better to use the IDverse. So filter, and then I think if, well, we can just pull it, and then well, I just assign it to the sub by WDT, and then so pull dates, sorry. Okay, let's see if it now, now it's working. So this is the 2nd of June, which is a holiday, the 1st of November, which is a holiday. This is a holiday, the 8th of December. This is a holiday, it's Befana, Epifania. I don't know, in English would be Epiphany, I think. This is probably Easter. Of course, we should check Easter. This is the 25th of April. The 2 of June, you see, it's working. It's just picking up. This is Ferragosto. So even if we didn't use, even we didn't know the dates of the holidays, we could just use this information to build the holiday dummies. And actually, we're already excluding the holidays falling on Saturday and Sunday, so that could be also a good strategy. They're all holidays if you check. They're like recursive. Of course, it's like it's not picking, for example, Christmas. So here's just picking the 26th, and that's because also we have the within year seasonality that of course is kind of is trying to fit the vacation, even though it's not fitting them really properly, but it's kind of fitting them. So it looks like it fits more the 26th than the 25th of December. And but this could be, as I told you, a strategy. We don't know, for example, which one of the, I would say that most of those would be negative, but maybe there are a couple of also positive values which I I'm not sure. Maybe we could just look at those. They're positive and those they're negative. So for example, we could just go here and select those for which this is less than -3, and they're whether okay, there are some missing observation. This is probably because, as I told you, while starting, probably the initial values of this auxiliary residual are not, I mean, are just missing because of the infinite variance at the beginning. Yeah, that exactly what is happening. So let's just skip those. So these are just the negative ones, and they're there are the holidays. Let's see the positive one. The positive one are just one. I don't know, for some reason it was more than expected on the 31st December 2023. But anyway, you see they're mostly of negative because of the holidays are having a negative effect. They're not all equal, but I mean, we could add many different single dummy variables, or we can assume they kind of have all the same or very similar effect and just build one dummy. So keep in mind, if you build one dummy for all the holidays, then you're assuming the effect is similar. And if you're instead using a dummy for each of these holidays, then it means that they have different effects. Maybe just to not to add too many state variables, I would just use one. But anyway, if you remember, we already had to do with that. And this is the Easter holidays. But as I told you, we can just skip this part. This would be the, let's say, the part where we put our information inside the data. But we can just, and that's exactly what we did while working with the Riemann models. So if you remember, we built a list. I built a list of all these holidays. And then I added the Easter holidays. And then we merge them into just one list. So of course you can do that and build your holidays here, but let's just skip this and just use the auxiliary residual to determine which holiday had this impact, such a large impact. Okay, and so we can create like the holiday dummy, and for example it would be just you exploiting our probably we can set all the yeah, that's a problem here. Of course we have this initial NA which kind of creates a problem, and that we wouldn't have of course defining the holidays, but let's just do something cheap from our work point of view. Let's start with this and then just substitute the missing values with zeros, and let's just do this. What's the problem? Dummy, sorry. I guess I misspelled something. A holiday, okay, holiday. Okay, so that probably we're just keeping the first time. Actually, this one here, the first 20, I think, two. Right, the first 22 observation. which do have some holidays, but anyway. So we could refit the model. Then I would add, if you remember, again, I don't know, we could add like a winter vacation dummy. How can we build it? For example, we want that between just to be gross without sloppy, without being too precise. We can make it start from the 22nd of December up to the 6th of January. So how can we do this? We can of course use the month. I'm not sure we don't. Yeah, lubricate we loaded. So month of how did you call the data set? WDT, sub WDT. So this is the data set we're using. So we're stealing the month from the date here, right? Just check it if it's working. Oh, it's not called date. It's already a date. No, yeah, it's already date. So I don't have to select. It's just a date. So month larger than, or actually, yeah, we can make larger or equal 12 times the month smaller or equal 1. So we're selecting just, so this is one, of course, if it's December or January. I could have put it just equal to, I mean, it's, no, actually, no, sorry, this is going to be stupid. This is stupid. It's in or, actually, or. So just put or. So this will be true if the month is either, we can just put inequality here, December or January, and then we want the day to be, no, I'm doing mess, sorry. If it's December, it must be larger than or equal to 22. So I would make times here. The day of the month, I think it's just day, for example. Okay, so day is work. So we want day of sub WDT is larger or equal to the 22nd. Okay. So it must be either December and the day larger or equal to the 22nd, or the month could be c'è lezione, sì, sono online in realtà. So January and the day should be either smaller or equal than the 6th. Is that right? Yeah, should be right. And for summer vacation, again, we could make something better than this, but let's just cut it short. That just take all August. Of course, all August wouldn't be correct. Usually we should take from the first weekend of August to the last weekend of August, and that would be mostly the most important vacation time for summer. But let's just make it simple. You can make it with more time, more realistic, and just take month of sub WDT equals 8. Well, we can make it as numeric, so I mean, it's not that necessary, but so it will become a number. Oops. Let's check it. Again, also this we could make as numeric. Let's just check for example if we're getting the right dates in both cases. So I would say let's check it by taking the sub WDT on those winter vacation. And if, yeah, we're picking the right dates, you know, it's from the 22nd. Again, the 22nd is not always correct. Also, the 6th is not always correct, because if there a weekend after that, then of course the holiday will be longer. But I just make it quick and dirty just to make it work. And summer vacation, actually, that's much easier. It's easier, but I missed it for some reason. Okay, because I already turned this into sorry, I turned this into a 0, 1, not a true false. So let's do one more page. Well, this is easy, so I mean it's okay. It's working. Yeah, we can turn this into 0, 1s, or if we leave false and true, they will be automatically transformed into 0 and 1. So it's really not that necessary. So what we do now is just let's take the model. So up here, take the model. We're just adding regressors, so we don't have to write a new update function, because that they don't change. No, they don't change anything in the update function. They don't change anything in the initial values. And so we just change the model, basically. Okay. So we changed the model. So this would be model 2. So instead of just going with load, we can add the, so we have the holiday dummy, then we have the winter vacation, we have the summer vacation, and here yeah, all the rest we can leave as it is. I mean, we could even put this variance to 0. We already know that this variance is 0, so we could easy up a little bit the estimation. But let's just, if I change those things, of course I have to change the update function, and so let's just leave it this way. I guess we can go on this way. Something wrong? There are different lengths. Yeah, it's just 27. Why is it just 27? Holiday done. Maybe I wrote it wrong. Holiday done. Is it just 27? Okay, sorry. This is why it's wrong. I use this as if it were something. This is already an index, so I'm using this in a wrong way. So sorry, I built this holiday dummy in the wrong way, because I'm already using the index. So This could be made this way. For example, so let's make it the right length. Let's write all zeros. And then let's just change the OO index to 1. Okay, this is a better way. Sorry, I was doing something stupid. Okay, this should be correct. You know, we have this some ones. So I don't know why I wrote those stupid things, but they were wrong. Okay, the model is now proper. We can go with the second fit. The model is now mod 2. Here, actually, instead of using the initial values that we prepared, we can just use the previous value of the estimate. So we can go with the fit 1. That would save some time. So fit 1 optim out par. That's where the previous estimates are contained. And we use the same update function, which we called update 1. So this is a little bit more involved, but not that much. So it shouldn't take too long to estimate. And hopefully we'll do a decent job. Maybe I should have left maybe the last month or so of observation for like for an evaluation set. That could be a good idea, but maybe we can do it next. So we are just using all the data, but of course, it could be a good idea to keep some evaluation set to see if the model is working. At least it's predicting well, it's forecasting well. Well, while it's still computing, I can already write the part to compute the smoother, which we're interested in anyway. The model will be the fit2 dollar model, and we want just the smoothing. Well, let's just compute the state smoothing for now. And of course, I will be interested in looking again at the components. Hopefully the components have a more meaningful meaning. If they're still kind of sloppy as the last time, we can use more data, but of course that would cost more time to wait. But anyway, we can go on with, again, plotting the time series from, in this case, well, from model 2, it's just the second one. And then just comparing that to the trend, which will be in smoother 2 alpha hat level. But then we may also check afterwards the average impact of those vacations. Of course, this way of finding vacation using the auxiliary residuals, it's fine, but you don't have the future of those. So you have any way to build the future of the dummy variables to produce predictions of the future. Okay. So anyway, knowing when the holidays are would be important for building future dummy variable values. So this was estimated. So let's compute let's see if the estimation went fine. Actually, in my case, it reached the maximum number of iterations. So it could be not in the like final minimum, but let's just go on like, pretending it's fine. You can see that from the message if you don't know how to interpret. Well, no, in this case, the message doesn't give you. But anyway, 1 means that maximum number of iteration was reached. We can also check the variances if we want. Well, the message is it's almost the same as the other model. So the slope doesn't change, and the 365-day seasonality doesn't change. So this is the smoother. Of course, there are initial value problems. I'm sorry, it's changed. We still have a trend, which is not a great thing here. And I will try to make a better model and put it on the web, on the e-learning page, probably based on a couple of more years. But I'm not using more years now because this computer will not be able to do that in a decent time. But I will put you in an R markdown with some comments and a better model. Anyway, so for example, how can we check the value of the regressor? Well, the regressors are just also in the alpha hat, and actually they will be constant over time. So if I just cut the alpha hat, for example, observation number 100, doesn't really matter because they're constant. They're on the top. So for example, this is the effect of the holiday dummy. So the holiday dummy decreases the consumption by 9,400 and something megawatt hours. Yeah, I think it's megawatt hours. Winter vacation has again a negative effect of 2,000 megawatt hour on the average, the whole period. And summer vacation have this, well, negative effect of 500 megawatt hours. Of course, this effect has to actually it's sum up to the effect of the within year seasonality. Okay, so this is the effect. I mean, it's larger than this, the effect, and it's also, no, sorry, it's larger than this, and it's larger than this in absolute value. This is instead a good estimate of that effect. All the other things are changing, but the slope. Oh, actually, the slope. We saw that the variance of the slope actually was 0, so also the slope is not changing. I'm just taking a single time point, but the slope is also not changing. So 23 means that it's slightly increasing. Why slightly? Well, because we're measuring this in thousands. So an increase of 23 per day is not very large, but it's an increase in the consumption. Of course, you have to think we are coming out of the COVID period where the consumption was like decreased, so it makes sense. And of course, as I told you, this is not a satisfactory model because of many things. Maybe it's a complex model. I could fix the initial values problem by giving better initial values than the infinite variance. I will make you an R markdown with all this commented so that you understand what I changed with respect to here, but probably also just adding some more years will help. But anyway, this would be the right way to work with these models and this kind of data. Of course, one could also try the sinusoid seasonality here as well. I don't think it will change much. One can play around with the number of harmonics and doing some kind of, I wouldn't say cross-validation, but maybe just use an evaluation sample to see which one is better. Think that the effect of this seasonality, you don't see it in the very short run prediction. So if you look at 1 day ahead prediction, probably you can even omit this seasonality because the trend is learning anyway, everything that has to be learned. But if you go with a longer time prediction, so longer horizon prediction, this component becomes very important, okay, the within year seasonality. So I'm not very satisfied about this example, but as I told you, I will fix it. But anyway, we built a reasonable model, and it's not working for various reasons, but I wanted to show you how to proceed using this kind of models for this time series. As I told you, this is a somewhat more involved the UCM class. So you see, we have to do much more work than using ARIMA, for example, but also most of the machine learning models. But it has those advantages that I mentioned. So missing values is not a problem. Forecasting and signal extraction you can do at the same time. You don't have to find different solutions for those two models. You can use them in things for problems that are just not forecasting problems. You know, we saw the polar poles problem last time. I also kind of explained to you another class of problems, like the problems that are called benchmarking. So rebuilding time series at a higher frequency from using exploiting the correlation with high frequency time series. And for example, that's another problem you solve in the same way using the same technology. So as I told you, it's more involved and delicate in some ways class of model, but it allows you to do many more things. And of course, we stop here with the linear Gaussian world of state space models, but there's a whole world of nonlinear or non-Gaussian or both state space models. And that opens up a large new world of studies, like probably I already mentioned Markov chain Monte Carlo methods, particle filtering methods. If you want to do nonlinear state space model, usually you have to go Bayesian, so using Bayesian statistics, which I'm not sure you're acquainted with, and then use all these computational tools that go under the name of Markov chain Monte Carlo. So there's still a large world of these models, even after Gaussian linear models. But already Gaussian linear models are really solving many problems. In my consulting, I used them many times. So okay, we could just maybe hide the parts of that, put to NA some of the data here and see how we would have predicted like last month of data. So for example, an easy trick to do this, for example, let's go back to define model 2. So we define again model 2. Before fitting, what we can do is we take the y, which is inside the model 2, which is, remember how many observations we have here. So maybe like the last 47 observation would be like 1.5 months. So we can set like from observation 1221 to 1247 to NA. Okay. And I will do an even dirtier trick here to make estimation quicker. I'll use the previous estimate to estimate this model again. This should be quicker. And I'll turn this back to 1. So if I put this on the e-learning, it still runs. Of course, it may take some time because we reached the maximum number of observations, so we're really not at the optimum, but probably we're very close to the optimum. But anyway, and I didn't pick up the BFGS, it would be the best algorithm for this kind of optimization. So I'm just redoing what we did before, but I set the last 47 days to NA so that I get a prediction of those data. And then a good thing to do would be adding here also the signal, because the signal is what I'm interested in when I do the prediction. Still taking a lot of time. Then while waiting, I'll take another example that I'll just illustrate to you without reproducing. And then I will put it on the e-learning. If it's probably it's already there, I don't remember. I wanted to show another kind of thing we can do with these models, but instead of producing that ourselves, I'll just give you the R markdown. Oh, it ended, so we can go on. Again, that was not enough to converge, but anyway, I mean, the values are still there. So this is the smoother. Now I asked also for the signal smoother, and let's just plot maybe the last observation. So from, of course, I cannot use this because they are missing. I can use those from the first one. So this is the prediction we want to produce, or the real data. And again, we can just use, well, the signal. Here we need the signal. The signal, it's mu, I think, if I'm not wrong. And actually, it's already univariate. And there's it's really bad. So I have to fix this model. Sorry about that. It's really bad. Probably picking just a random walk would have already made that better. But anyway, so I don't make those examples before I don't check those. I mean, I have many that are working, but when I come here in the classroom, I want to pretend I never did that, and we built together the model. So sometimes things go wrong, and this is just one example where thing went wrong. But I will provide you with some fix to this example so that it works. I don't want to spend that time. But what are the problems here? Probably the initial values is an issue. And in real projects, the initial values I don't put to infinite. So I don't use that infinite variance condition, which may be very dangerous. but I use like initial values coming from an approximate linear model first. So maybe I use like a linear regression on a flexible trend, which could be like I don't know, splines. I don't know if you ever used splines of the time. Then I use the sinusoids maybe for the 365 days and the dummies for the 7 days. So I have initial values for all those components, and then I put those initial values inside the state space form, avoiding the infinite value. From a rigorous point of view, you should not do that because you're using the data twice, but we don't want to use, we're doing no tests or no formal things here. So we just want to have decent forecast and decent estimation of the components, and that those pre-treatments or those finding initial values in a better way using values would make things work better than what we're observing here, okay? So this is pretty bad. So using this as example, I'm not convincing you that this class of models is a great choice. We'll fix that. But I wanted, to do these things together so that you know how to deal with those things. Of course, this is a complex time series. Things can go wrong pretty easily. So the example that I wanted to show you, again, this is another application of UCM, not for forecasting. Actually, you can always use it for forecasting, but the application that I'm going to show you is a more policy evaluation use of these models. I guess I have it here. Is in. So this is the example. So let's just go through this. Oh, it's in Italian, of course. I'll put the English translation. I'll put the Italian one and the English translation. So this is a time series of car injuries in Italy. It's a monthly time series. Okay, yeah, I did this before the book, so it stops at 2014. We could, of course, maybe find more data and go on. But the interesting thing here happened on 2003. I don't remember the month, could be July, but anyway, it's written here. So this is the number of injured people because of car accidents in Italy, okay? Per month. So it's a monthly number. I mean, it's a large number. The first thing we notice, it's okay, it's decreasing. That's good news. But the point is that on, I think July, let's check it. On July 2003, I think it was July. Yeah, on July 2003, the scoring system of the driving license came into work. So you probably all know what a scoring system for driving license is. If you have fines because of moving traffic violation, you lose points from your license. I think in Italy you start from 20, and if you reach 0, you lose your license for a while. And that new system came into work in July 2003. If we look at this time series by visual inspection, we don't see anything particular going on around 2003. Well, maybe this shape, if you're a good observer, maybe the shape of this year is a little bit different than before and after. So, but you have to be a very good observer, okay? Anyway, the problem is the following. We would like to assess if that policy had an impact, if, for example, on injuries. Oh, I could have picked the accidents. Well, accidents probably that doesn't. I mean that. Yeah, probably that could also impact the number of accidents, but it could also impact the how bad the accidents were and so on. So I just picked up the injuries. So I remember that the question after a while was, there was a clear impact at the beginning because people, of course, were more afraid of lose their driving license. But then, of course, as often happens in Italy, the controls were not that strict. And so this fear of losing the license kind of faded out. And so there are two hypotheses we want to test. One is, did the policy had like a permanent effect? So it made the time series jump down and stay down, or did the impact of the policy just take the number of injuries down for a while, but then slowly going back to the previous value? And you may say, okay, how can we do that using these models? Of course, we need a model for the time series, and here it's pretty simple. It's kind of like the air passengers. I think, yeah, I did the usual means versus standard deviations plot, and it's moderately increasing, so it means probably it's better to work on logs. I mean, it's not that strong. It could be working also on the real values, but okay, I think I worked on log here. Okay, so actually I worked on log times 100. I told you that sometimes it's better to multiply by 100 just for numerical reasons. Okay, so this is just the log time series. It's not very different than the original ones. So it's a very seasonal time series. It has a trend, so it's very easy. We should probably use like local linear trend plus here, local linear trend plus, in this case, I just used the dummy variables, stochastic dummy variable, seasonal dummy, and I fit the model just using some initial values. I didn't have to write the update function because these are just variances on the Q and H matrices, so that have to be estimated. Okay. What comes out at first, so this is just the basic model we're using. We're not modeling yet those changes, okay? Again, we have like the level that has a positive variance. The slope doesn't seem to change over time, so it's like a random walk with drift. The drift, of course, is negative. And then we have the seasonality that is not evolving, so it's kind of staying the same. And we have strong observation noise. So of course, there's a lot of noise on this time series. Of course, the weather may have big effect. The number of holidays in a month may have an effect, and so on. But what I do here is to compute the disturbance, disturbance smoothing, sorry. So the state and this disturbance smoothing, but here I'm interested in computing the auxiliary residual for the level. Okay, here I use the formula. You can use, of course, the R standard formula. Here I just, maybe I'll just substitute the R standard. This is the, let's say, the hard way to compute the same thing. As I told you, we have two kind of variances when it comes to disturbance smoothers. So the variance when you are using the smoother to estimate the real eta, or the variance of the disturbance smoother, and this is the variance of this is how you pass from one to the other one. But anyway, I will substitute this with the R standard function. It does just the same thing. So I'm just looking at the auxiliary residual of the level. Well, here I put the line I'm using the like a 1% alpha to build this confident interval. So it's not 3. I put it between 2 and 3. Probably this is minus 2.57. But anyway, even if you put it at 3 as we did, well, at 3 we find just one jump here. If we put it at 2 point whatever, there's another one here. But anyway, we clearly find a strong effect on the level that is jumping down, because this is the auxiliary residual of the level disturbances, okay? So the level is jumping down. And when is the level jumping down? So I just taken out this information. It's June. Is June correct? Yes, June is correct, because if you look at, again, I already told you these things, but if you look at how the state variable is made, the state equation works, so if something happens on eta on June, then the data will see it on July, because the effect will be on the next state variable, okay? So the fact that this happens on June is correct. So the new policy entered into work on July, and we see that on June. So it's as expected. Okay, so here there's the new thing that it didn't. Probably you have to go through this a little bit to understand it. So we want to model 2 effects. The first effect is very simple. It's the effect of the step variable. So the step variable, if you remember, is just a variable that is always 0, and then it becomes 1 starting from the date of the event. So the S variable is just 0 before July 2003, and it will be 1 starting from July 2003. And this will catch the permanent effect of the policy, okay? If the policy had a permanent negative effect on the number of injuries, I expect the regression coefficient lambda to be negative and to be significantly negative, okay? But then I want to model also what I call the transitory effect. As I told you, everybody observed this. Yes, starting from July, everybody was starting to drive very politely and very respecting the laws. But then, as the time passed, the control were just limited as they were always being. And so people were going back, or drivers were going back to behave kind of what they did before the new policy. And so this is the transitory effect. And the transitory effect, I have to write something here to make you understand how we could model that. So, so we want to model the transitory effect this way. And I will have to convince you that in this way, we can model a transitory effect. And this is just like an indicator function for the t equal to tau, where tau is the time in which the change happens. Why is this working? Okay, let's suppose, first, of course, we assume that Wt is 0 for t less than, well, if we leave this, actually we should write t equal tau minus 1, because it's having effect on the next day. Okay, so it would be so I'll try just to show you how this thing works. So this is like WT, and this is the time, and this is like, well, this is tau, but as we're actually more interested in tau minus 1, because as I told you, if I model it now, the effect would be the next month. So we start from 0, okay? Because for t smaller, well, actually t is smaller than tau minus 1. So this starts from 0. Then we have this tau minus 1 moment, which would be June 2003 in our case. And what happens? WT plus 1, so this would be, make it this way. WT plus 1, when it's tau minus 1, goes to omega. Is that right? Why it goes to omega? Because this goes to 1. This is omega. Well, this is still 0. Delta times 0. This is delta times 0. So starting from tau, because this will be tau, so TP plus 1 in this case would be tau. Well, sorry, maybe I should write it here this way. Let's just leave it not minus 1. So actually starting from tau, because the effect will be the next day, this goes up to omega, okay? So because this is 0, the first part is 0, and the second one is just omega. Let's go one step farther. Let's go to tau plus 1. Well, this goes back to 0, so this effect goes to 0. But then we have delta that multiplies omega, the previous one, which is omega. So we have like here delta times omega. Then you get to the next time, and we have delta that multiply the previous one. The previous one is delta omega, so we have like delta square omega. And why I'm putting a delta, why I put a decreasing? Because delta is generally, well, they should be between 0 and 1, okay? So if it's between 0 and 1, the powers will be smaller numbers, and so on, okay? So what we observe is exactly what we need. It's like something that jumps up at tau, but then slowly goes down. So this, for example, these are called transfer functions. If you look at literature, transfer function modeling, you can apply this, of course, to ARIMA models, also to any other kind of models. This is one of the simplest transfer function models. For example, now we will be using that for modeling this temporary change of the effect of those policies. But for example, to me, it happens to apply that often in marketing. So, for example, I'm doing, as I told you, I did a work for Unieuro, and I have to model the response of an investment in advertisement on different channels on the sales, okay? And usually advertisement has a similar effect. So the advertisement is probably a big impact while you're advertising. So for example, Unieuro gave me weekly data. So that's on a weekly basis. So on the week in which you're advertising something, your sales go up. But then when you stop advertising, maybe for a few weeks more, you see a smaller effect, but you still see the effect of those advertisements, because it's natural that not all of the people will respond immediately to your campaign. Something will be like waiting, I don't know, the next weekend or whatever. So usually you have this effect of a dynamic effect of advertising on sales. So this is a model where that actually you can apply in many different situations. And as I told you, this is the class of this model, which in some things are related to ARIMA models. I think, yeah, I think I speak, I give some space about these models in the book. They're called transfer function models. Okay. Sometimes they're also called dynamic regression models. Why dynamic regression? Well, just because so if this is, for example, this is our dummy variable, but it could be any regressor. So for example, in the case of Unieuro, they gave me the amount of money they invested. So I don't have a dummy variable. I don't have the variable. I'm advertising. I'm not advertising. They are just telling me how much money they put on advertisement in that month. Okay. So you can also apply not just to dummy variables, but also to continuous variables. And why dynamic regressor? Because it's just like a regression, but the effect of your regression is not static. So it's not at time t that your regressor xt has an effect on yt, but also on yt plus 1, yt plus 2, yt plus 3. So that's why it's you can see it also as a dynamic regression. So this is, as I told you, just a simple version of the transfer function model, but it's probably the most used transfer function model that we can exploit here. Here. And of course, you have to find a way to put that in state space form. Again, if you have the constant C and D that you have in some other software, you may exploit that constant. In Kvass, we don't have that. And so I kind of have to made up a different way to build that transfer function. So as you see, this is the transfer function. I just called P. P is just like pools. A dummy variable, you can call it also a pools variable. And S is a step variable function. So here I just written the same thing I wrote on the OneNote pad. And well, here's just a description how you could produce that in a state space model. So you start with a state space model where the observation, well, you just multiply 0 by that alpha, so that extra state variable. And of course, the alpha starts from 0 and goes on because, no, actually, the alpha doesn't start from 0. I mean, the alpha could be any value because you're multiplying here by 0. Can't I highlight that? But anyway, I don't know if you see it here. I'm multiplying by 0. So whatever alpha is, I just put it to 0. But then starting from tau, and here, look, the alpha is just a constant. So actually, we will see that this constant alpha at the beginning will be coincident with the omega 0 there, okay? So it's just an omega 0 that first is put to 0, okay? Then, after the event happens, you see that this goes to 1. So where this was 0 and now it's 1. And instead of having the alpha that produces itself in the future, we have this delta that is multiplying the previous alpha, okay? And so the initial value actually of this alpha will be exactly an estimate of the omega 0 here. So omega 0 is like the immediate impact of the advertisement, or in this case of the policy. And then we have like the policy that decreases its effect according to delta. Of course, the closest to 1 is delta. The slower the downturn, and the closer of delta to 0, the quickest will be. And here, I mean, it's just coding, so you may just take your time to read it, but I implemented exactly that thing by using the SSM custom, of course. And let's see what happens. Well, these are the variances of before. And look at this. This is the estimate of the delta. The delta is 0.7. So it's, of course, how quick is that? It means that every month it reduces the previous value by 30%. Okay, you can interpret it in that way. And here, so this is the effect of the step function. So the permanent effect. You have to think we're modeling in log times 100. So 5 here means 5%. So it looks like there is a permanent effect in the because this is the S variable. This is the regression coefficient of the step variable. So it gives us the impact that is permanent because this is the step variable that is always there. And so it looks like the permanent effect is minus 5% circa. Of course, we could test if that is significantly different than 0. This is the transitory effect, which has to be summed to the other one. Okay, so the immediate effect is minus 12% plus minus 5%. So the initial effect of the policy is minus, I would say, 17%, but a good part of this initial effect just dampen out in very few months. I would say the next year is virtually 0. It takes just few months to go back to 0, but there is a permanent effect of 5%. So the initial effect was 17, 18%. That then in the long run goes back to 5%. This is the sum of the two components that gives the complete effect of that policy. So minus 17 or 18%, and then goes up and remains minus 4. So there's a temporary part, but it's also a permanent part. So at the end of the day, and I mean, they kept it, but I guess all Europe has that system. Probably it worked. It reduces by some measure the number of injuries. And this is the log 100 time series. So the blue one is the level without the change, and the red one is the level with the change. So you can also have like a counterfactual. If you measure the difference between these two lines, it's the number of injuries you're saving because of the policy. Actually, this is not the number because it's in log, it's the percentage. So the difference of these two lines is the percentage of injuries that you're saving every month because of that policy. Okay, so it actually worked. And this is, okay, so this is back in the original unit of measurement. So you should see I take the exponential and divide by 100. And so this is here you can count the difference between two lines, and that would be the number of injuries that you saved because of this policy. And this is, yeah, exactly what I said. So this is every month the number of like saved injuries because of the policies. And of course we could test if, because of course this is an estimate, a statistical estimate, so it could be, it has a lot of uncertainty. So we can test if the lambda is the permanent effect. So there is no permanent effect against there is a negative permanent effect. And this is just the p-value, and actually the p-value is larger than whatever, 5%, even 10%. So it looks like the temporary component is not so certain. I mean, the estimates are indicating the best estimate is minus 5%. But statistically, that minus 5% is not very different than 0. Okay. So there's a lot of uncertainty about the permanent effect. There is no uncertainty about so this is the omega, so the temporary effect. The temporary effect is certainly there. This permanent effect maybe is not there. Okay, so this is another use of this kind of models. And of course, I didn't take enough time to show you how to put everything in state space form. Maybe, I mean, here there's a long explanation. I hope if you're interested in, of course, you don't have to do this on the data set. that you will have to work on for the examination, but I don't teach for the examination. I teach you to show you what kind of things you can do with this kind of models. So there are many, many different things that you can do with UCM. There are something that are answering to more complex questions than just forecast this time series, okay? For example, this could be something hard to do using machine learning. So machine learning is not like exhaustive of everything you can do with time series and with statistics, okay? So it's good for some things, but it's not good for other things, okay? And there is another, I guess I can put it, if it's not already there, I have to check. Another example where I do something similar, actually the same kind of models. Instead of measuring the impact of a policy, I measure the effect of terrorism on the flights, number of flights here. This is very similar. So I can translate them and put it on the e-learning. This is flights, international flights to and from Australia. It's also a time series you can download very easily because it's public and it's very long. Again, I did this for the book, so it stops before 2015. But here, actually, you can see very clearly here a jump down, a downward jump in the flight. This is also 2003, and maybe you can see here a jump. It's not so strong, but there's a jump here as well in 2001. So we have the 9/11 effect on fear of flying, but even more than that, there is the war in Iraq. That also started, I think, in March 2003, if I well remember. And again, we could see, again, if there is like, of course, the impact is temporary. I don't have like, I didn't put here a permanent effect component. So I just used two temporary components to measure how long and how strong the impact of those two events had on the flights. And if you, again, I work on log because of this indication here, 100 log. Again, we start with a simple, it's a monthly time series, so we start with a very simple model, which is the same model as we used before. And again here, well, these are the auxiliary residual of the level. Okay, we see some kind of strong effect here. This is, I would say 2001, and this is 2003. So we see this kind of change, but you see also a reaction. I mean, you see a downward jump, but an upward jump in some way. So this could be indicating what I've just said. There is an effect, but this effect eventually goes back. And you see it in the disturbance as well. And you can see also the 9/11, it's even quicker. So this is the downward jump here. And here's the more upward jumps that is kind of making the time series back to its initial level. And if I look at the large jumps, just looking at this, you get September. Yeah, of course, September, you may say, okay, but I already added one. Okay, that's why. So I already added one here. So these are the right dates. So September, actually here starts from, we have two big jumps. One is already in February and one is on March. Because of course, if you go back to maybe Wikipedia, the war in Iraq started with some ultimatums. And of course, so you know in advance that it were probably going to be dangerous. So we also have the partial effect on February and then also on March when the war began. Again, we apply the same kind of models that I just explained to you, but we use twice. We use two of them. One for the 9/11 here, and one for the war in Iraq here. So we are just adding two of these transfer functions to the model. And you see that you can, of course, I'm just going through very quickly. I want you more to understand what we're doing, that the technicalities that you can take your time to understand. So this is, for example, the effect of 9/11. It's very quick to go back. The delta was the delta here was so it was again 0.75, so 75% decrease of the effect. I mean 25% every subsequent months. The effect goes down by 25%. Okay? So the complement. It's slower with the Iraq. We saw that from the plot. So the Iraq war decreases by about 13% every month. And indeed, so this is the estimate of the 11th of September. So this is by percentage. So had a momentary decrease by 12%, but it goes up to the previous situation rather quickly, maybe in 1-2 years, 1.5 years, something like that. A little longer, you see the Iraqi war. So the effect is also larger, minus 15%, and this was minus 12%, but it was also clear from the plot. And also the speed of decrease or going back or to the previous values is slower. So this kind of model, here's the comparison of the two. Okay. Okay, so a similar example. Oh, this is the cumulative effect. I'm just accumulating the effect. So because of those two events, the number of passengers was in total it was like 50% less and 100% less. Yeah, I wouldn't comment much. This is not. I mean, this should be applied to the number of passengers, so to estimate number of passengers. And again, here we have like a the counterfactual. So the blue line, it's what would have been happening without those events, and the red lines are the actual levels because of those events. And again, we can test. In this case, both changes were very significant, and that's it. Okay. So I would say we close the unobserved component model part right now, unless there are questions, but I'm sure there are not questions. I mean, from home, you even have less question than from in presence. So if you don't, and actually, even the people from home just decreased. Terrible situation. So I guess I told everything I wanted to tell about UCM. I would just add this comment that I already did, but maybe we can formalize. As I told you, usually when we have non-stationary variables, we set the initial condition, usually the mean, we set it to 0, and the variance, we set it to infinite, okay? If you have few non-stationary components, that's fine. If we have so many as we have, for example, for the electricity load UCM, that can take many observations before the filter, but at the end of the day, it has also an effect on the smoother we have seen before it becomes a reliable measure. So, as I told you, what is my strategy if I have to write, for example, a software? The problem, I mean, if you can work on your own model because you have just produced prediction, you can like, okay, adjust everything by hand until it works, until you get an interpretable result and so on. So you can try different values of the initial value, substituting this infinite, but also probably this initial zero. And we can reason about how to do that. But of course, if you wanted to produce a software that it's working without any human intervention, you have to find strategies to do that. And for example, a strategy that I do use very often, if I just to then provide a software to somebody that has to put it into its own process, and the software has to work. It doesn't. We don't want that to stop because our part is doing crazy things. Is I usually do this. For example, we were doing a model where we had the trend, we had two seasonalities. I may just start with a regression model. And as I told you, I will put maybe a flexible component for the trend. So I often use, I don't know if you ever, so we can also check them up. It's something you should know. The splines of T. So splines are just, I'll give you some more information. If you don't know splines, splines are just transformed of your variable, in this case of T. So you get like phi of T, phi1 of T, phi2 of T, and so on. They're just known transformations of the sign. You could also use, for example, you could use polynomial, like, okay. So that's another way to build a flexible trend. Splines are usually better than polynomials, even though they're related to polynomials. So they're just transformation of the variable you pass. In our case, it's just the time. That makes you can make a linear regression nonlinear, okay, because of this transformation. Then we could use whatever we want, like either dummy variables, for example, for the 7 days so the 7 days, actually 6 dummies are enough for the 7 days seasonality, and we can have, like we did, like for example 16 in our case, but sine and cosine. Of course, we have regressors here. Sorry about that. So we can call this delta J. We can call this alpha J cos 2 pi divided 365 JT plus beta. And of course, it's a regression. We will also have the noise, okay? So what I usually do to get initial value that are safe is I run a regression of this type. It's just a linear regression, so you always get results from this. This doesn't fail, okay? But then I have, of course, if I set t equal to 1, it's the situation for the initial values. I have initial values for this dummies and this cosine and sine, and of course there. And I also have like the uncertainty because my alpha and my beta and my delta, they also have standard errors. So I can just use this delta, this alpha, this beta as initial values and put like 3 times, for example, the standard errors that I have from the regression estimates to get some uncertainty about them, okay? Of course, they're not moving in time, they're just deterministic, and we will be using usually time varying components, but it's fine. It's just a way to have initial starting values that are okay. What about the trend? Well, the spline will give us some kind of trend, so we will have like a trend, which will be just some, again, it will be just a sum of some regression coefficient by whatever transformation I use of the time trend times, and this will give us the trend. And of course, we just can observe the trend at time equal to 1 and say, okay, my level at times equal to 1 is that. And what about the slope? Well, for the slope, for example, I can take the trend that I estimated at time 2 minus the trend and estimate it at time equal to 1 and fix it to the slope, an initial slope, okay? So this is, for example, a strategy that I use for building initial values. And of course, for a dummy variable, you have to check in which month you find yourself in t equals to 1 and pick the right one. And the other ones are just lagged version of this. And for the sine and cosine, well, this is, of course, the initial value for the sine and cosines will be alpha j's times the cos of 2 pi divided by 365 times 1, no, sorry, times James times 1. Okay. And this, of course, for every j, and this is good for the sine. So this is my strategy to make initial values that are good enough so that the smoother doesn't fail the common filter. I'll give you just one more word about splines. I mean, we will end with splines. I don't want to start today with the machine learning parts of this course. So splines are a very, I would say, powerful Okay, now it's good. So I said splines. Okay, splines we can use in linear regression. You can use in ARIMA. We can use in UCM. And splines are just, as I told you, a simple way to make linear things nonlinear. So suppose we have like an x and a y, and we want to model, so a typical regression of y on just one x. Of course, we may have many x, but it's easy to explain that just for one x. So like we have some points, I don't know, that goes like this, okay? And we want to fit a smooth function that goes through these points. So ideally, we would like to, I mean, just by, if I do this by looking at the data, so the Matteo Pelagatti regression will be something like this. So this is my objective, to come up with something like this red line by just using a linear regression. Okay, so the splines are made this way. Suppose, first of all, we need to split the range of x into sub intervals, okay, into intervals, okay. So for example, I'll just take two intervals here for make this simple. I'll just make an interval from the beginning to here, for example, and from the beginning to here. I just divide it in equal proportion. They don't have to be equal, of course. These are called nodes. So this would be nodes one, node one, as in this will be node two. And then of course there are the ends nodes, because of course it's like a natural initial node, and this would be like a natural final nodes. So I just decided the central ones and the other ones are like natural nodes. So how does a spline function? Let's start with defining what a spline function is, and then I will tell you that those class of functions that we're about to define, they have a basis basis function that reproduce those functions, okay? And that those are the ones we will be using. So the idea is that I want to run like tree regression. I have three intervals here. So I can run tree regression, for example. Usually we use cubic splines, meaning that we run local regression on cube. So we take like x squared, and x cubed. But it's like we want to run the regression on the three separate intervals. But of course, if we go with just three separate regression on a cube, we would have probably non-continuous things. Probably I would get something like this here, well, something like this here, and well, here something like that. So it wouldn't be continuous on the nodes. There will be jumps on the nodes, but I want a continuous function. So I have to say I want to run three separate regression, but on the nodes, I want a continuous line. So it's like tree regression with a further constraint, and the constraint is telling you here in this point the two regression here have to be continuous, and the same happen here. Well, this is easy here, okay? So it's like tree regression with the constraint that the function that I'm building has to be continuous on the nodes. But not only the function has to be continuous on the nodes, also the previous derivative. So if we are using cubic splines, I'm asking also that the function is continuous, the first derivative is continuous, and also the second derivative is continuous. So I'm building a function that is extremely smooth on the nodes, okay? And indeed, if you do this, this thing here probably gets something like this, a very continuous smooth function going through the points. And this is just the definition of a spline function. What is a set of basis function for the splines? Well, it's just the set of x transformations, so transformation of the original x, that will give you will span, you say this will span all the set of functions that have this characteristic that I have just described. And it's very easy to build them. I don't want you to explain you how to build them. You can find them everywhere. But the point is that from the x, for example, in this case, I would need to build. Actually, I forgot how to compute the number of spline bases, because it depends, of course, on the number of intervals, but then of course it depends also on some assumption on the initial and final nodes. I guess this would correspond to 4 basis function, but anyway, it doesn't really matter. It means that if I will have a set, if I call S of X the set of splines functions, the set of all spline function with the same nodes. So of course it depends on the set of nodes. I know how to write this as a linear combination. It will depends again on some, I would say, big J dependent on the number of nodes. And it will be just like a linear combination of this spline function, which I just call psi of x. Okay, so this we compute before. It's just like computing powers. They're not powers. They're just other kind of transforms. They will look like. They tend to look like this. Like, well, the initial, the final spline function look like this, and the central ones usually look a little bit like Gaussian densities. Okay, they tend to look like this. And why do I show you they look like this? Because it's important they look like this, because they're kind of localized, meaning that it's just like every single basis is just like taking care of fitting the function in that area of the plot. Okay, so they're different from, for example, polynomials. We know that a polynomial can arbitrarily well fit any continuous function on an interval. You know, that's Weierstrass theorem. But the problem of polynomial functions is that they're global. They're not. They're trying to fit the whole. Every single function is trying to fit. Every single base is trying to fit the whole function. Here, every basis function instead is trying to fit a part of the function, and actually, so it's indeed you could choose where to place the nodes in a way that in some way is rational, meaning that maybe you want to have a node where there is a a change in the shape with respect, for example, to a cubic line. So you can reason about where to put the nodes. And actually, this is another interesting thing about this basis function, is that if you put more than one node in the same point, I could put like 2, 3, 4 nodes in the same point. Every time I put an extra node in the same point, I'm losing the continuity with respect of one derivatives. So if I put 2 nodes here, I'm saying I'm just requiring the first derivative here to be continuous. If I put 3 nodes here, I'm just asking the function to be continuous. If I put 4 nodes in the same point here, I'm telling you can have a discontinuity in that point. Okay, so you can kind of fix the nodes to better fit the function if you have some information about that function. Okay, otherwise, anyway, you will get basis function of this type that will, each function will take care of approximating that part of the function that on the interval, but the summing up all this function will make anyway a continuous function, a resulting function. Again, we could play around. I mean, in R, we have actually one of those packages that you always have inside your distribution, which is called splines. Just to show you some simple example. So, for example, let's just build something like this, like a continuous function we want to fit. Like we could take a cosine function or a mixer, a cosine plus some linear trend, whatever. Maybe let's just build an x that goes from 1 to 100. We can build like, let's call it f of x. I don't know, a cosine of 2 times pi, I don't know, divided by 100. times x. And then let's just build a y that adds some noise to the function, to the discontinuous function. Of course, the noise, I don't want it too big because this goes from -1 to 1. So I don't know, maybe it's just with the standard deviation equal to 0.5. Let's see if it's something reasonable. Sorry, I'm missing the 100 here. I'll set a seed so everybody can then reproduce the same example. So these are the points, and this would be the continuous function. Oops, f. Sorry. Okay. We can also make something more interesting. Like we add also some like linear trend, just to show you that splines can also model trending variables. They really don't. So maybe I just like something like this. Too much, too strong. Let's make a smaller trend. Oops. Yeah, I don't want the trend to dominate so much. Okay, so this is a nice, very noisy function. You know, there's a lot of noise, and it's a continuous function. How do we create spline basis? Well, as I told you, there is this library called splines, which is always loaded into R, but there are libraries also for that in Python. And for example, the functions that are usually mostly used for building splines, it's called BS, basis splines. So spline basis is BS. For example, I can build an X, so this would be a matrix of spline basis. There's some of the explanation. You can either decide where to place the nodes. So we could place some nodes in specific points, of course, between 1 and 100. Or the degree by default is 3, meaning the degree of the polynomials we're fitting. So usually we use cubic splines. But if more easily, if we just define the so-called degrees of freedom, so how many variables, so how many basis functions we want to generate, we can just specify the number of degrees of freedom. I don't know, maybe I just want 3 or maybe 4 bases. And in that case, this function automatically looks into X and divides X in a number of intervals with the same number of X observations. Okay. So if you look at X, just have a matrix. We created 4 regressors, as I told you. They're just transformation of the original X. And if you want to see how they look like, you can like go with matplot of X type line. And they're kind of how I just showed you. Okay. If you don't specify any other things, these splines are built assuming you will use an intercept into your regression model. So otherwise, you can say if you want really to span a space where the intercept is arbitrary, you can say that into. I mean, there's a parameter where you can specify that. But apart from the final node here, for example, you see that those functions are kind of localized. They overlap, but the more you create, the less they overlap. And of course, they have to overlap to create the continuity. but every single function has like a more specific look at one part of the x, okay? And for example, let's just do a linear regression. So I will call it reg of what? Of our y on, and sorry about that, I have to look for some tilde. Here, no, here I don't have tildes. I can steal it from here. So I just regress this on this x. Okay, let's compare. But we can compare the data, but we can just steal this and add the regression line, or the regression curve in this case. It's not. And so we put from reg, we steal the fitted values, and maybe we can make a blue line or a blue curve. Okay, well, this is excellent. Of course, the highest variance of this estimate is on the beginning and on the end, because you don't have future values. You can only base. And in some cases, I don't want to give you too much information. Splines have also relation. We could estimate some kind of splines also using some modeling state space form. So there is a relation about that, but it's not what I'm interested in here. So we are just using linear regression. We are just using transformation of the original x into a set of basis function that spans the space of spline function. And spline functions are functions that are extremely good approximators to any kind of continuous function. Okay. If you want, this is also already putting the first feet into machine learning, because in some way machine learning is just using different basis function to approximate functions. Okay, and the sets of spline functions could be a set of. I mean, neural networks usually use different kind of function. They use like sinusoidal functions, but it's just a different set of functions. But we're doing something close, or we're just using a linear model or nonlinear transformation of the x variables. This you can use inside the regression. You can use it as regressors for ARIMA models, for UCM models, and whatever. Okay. And I will tell you also one more thing about this function. You can also make splines, periodic splines. There are other libraries for making periodic splines. What's a periodic spline? It's simple. It's just a set of splines where you introduce continuity here and here. If you say there is also continuity between here and here, if the x is larger than this, it's like I go back here in some way. Okay. Then I'm producing in some way a periodic spline. And that could be used for seasonal. It would be another kind of seasonal component that we could build. Okay. So spline functions are really a powerful tool. If you don't know them, try to become acquainted. I used it in many situations, and you see, this is it was a random example. I didn't put too much reasoning about how I built the data, but it's incredible how well we're approximating this line by just using this very noisy data. These points are, I mean, they're not close to the original one, but we are estimating that as well. Of course, here is a typical situation where you can decide the number, for example, of degrees of freedom, so the number of bases, and you can use cross-validation, for example, to decide the number of basis functions, and so on. Okay, I'll just stop here. And starting from next lesson, we'll just try to, I will not explain you machine learning because you know it better than I, because you've been going through one and more years of doing machine learning, but apply machine learning to forecasting is something that has to take many, have to solve many issues before you can use it for forecasting. And so we will be more analyzing the features or the transformations, so building features for machine learning that are good for those machine learning models for forecasting, and eventual transformation of data sets for applying machine learning on forecasting. So that machine learning you kind of know, you know actually very well. We'll just adapt it to our problem, which is a particular problem. It's not just a like a cross-sectional data set problem. Good. We stop here, and so see you on.